any sufficiently advanced technology is indistinguishable from magic.
Open the pod bay doors, Hal.
Guest is really a wonderful and delightful writer and a fellow podcaster and author. A wonderful, wonderful author of many books about Dirac, books about Churchill, books about the universe. And today we're going to be talking about this book, and we're going to schedule, 5 more parts, 5 more episodes. If Graham will beg me his forbearance or my forbearance, I don't know which forbearance we'll do, but Graham Farmelo, thank you so much for joining us. How are you today?
I'm very well. Thank you for having me on. It's a pleasure.
My motto of my channel is always be curious, ABC. And I think I will title this episode From Newton to Nima, because we're going to go from this little man here. This is supposed to be Isaac Newton, a finger puppet of Isaac Newton.
What?
And
I see the one. I'm sorry. It looks like Einstein, but I see he's holding Newton. Yeah. Okay.
Yeah. I have an Einstein. Einstein is he's over there. I'll get Einstein later. But there's this is Isaac Newton. He's not a good representation. But Nima doesn't. They don't have one for Nima just yet. But these finger puppet manufacturers, they're a little bit behind the times, just a couple hundred years or so. So I want to talk about the universe speaks in numbers. There's a theme that runs through it, and I've been talking a lot on my podcast, Into the Impossible, about the difference of opinions as to whether or not, first of all, we need a theory of everything, whether a theory of everything is a proper scientific discipline. And my first question to you is sort of a pun, but it's sort of a truth hidden within the pun. And that's, I wonder, Graham, sometimes are we putting the toe before the gut? In other words, we don't have a grand unified theory, as far as I know, that everybody agrees upon. And yet we're kind of obsessed with a theory of everything that unites all 4 forces. Yet we don't really have a very strong inkling of how to unify the 3 strongest forces. What do you think about this notion that we're obsessed with kind of skipping the gut and going straight to the toe?
I must say, I think there's a danger here of over-dramatizing what physicists are seeking to do. I must say straight away. I mean, I like all authors, it's very tempting to go with these brief acronyms and these big ideas and what have you. But I'm much more comfortable myself with if you like a plainer statement of what I believe physicists, theoretical physicists, are seeking to do, with, of course, experimental physicists. What I think we are seeking to do is find a theory of the most fundamental interactions that we know of in nature. What do we mean by that? I mean interactions where we don't know that they are built from something deeper, so to speak. In other words, things that we find as fundamental and the most fundamental entities that we can identify. Now, you could never put that on a T-shirt. I realize that, but basically, we're talking about the strong, weak electromagnetic interactions, and the thing that looks very different superficially, which is gravity. Now, physicists of this kind of persuasion are very, very focused on the understanding the smallest possible, the largest possible, so the cosmos and the very smallest. But following my late friend Phil Anderson, I really do think it's important to bear in mind that even if you have the standard model in all its glory, remember it's how beautifully tested it is, you still can't predict the shape of a cauliflower, for example. Mm-hmm. There are things you can't do with those fundamental theories, or no one knows how to do it because there are other principles that other types of physicists look at. Now, I do believe that there is such a thing as a fundamental branch of physics, but I do think it's important to have some humility and bear in mind that we're not talking about the whole of physics here. We're talking about actually quite a small, but in my opinion, very significant proportion of the whole activity of physics, right? So, and I think that it's overplaying it to think that we ever or rather, certainly in the immediate future, come up with a theory that you can write on a T-shirt or what have you, that from which everything else will plainly follow. I think that is overselling it, frankly.
Yeah, I was speaking, of course, about my past guest Michio Kaku, who's been on the show and is gracious and kind and likes to talk and promote the God equation, and we can talk about God, of course, as Isaac Newton was wont to do. And I love the quote that you have in your book, kind of a pertinent to sort of this notion that we talk about nowadays, the imposter syndrome. I did a podcast with Barry Barish not too long ago that inspired my next book, which is going to be called Think Like a Nobel Prize Winner. And Barry told me he had the imposter syndrome once in his life. And I said, you got to be kidding me. That can't be anymore. And he's like, no, I feel it even more than ever, because when I got the Nobel Prize, I had to sign this logbook saying I got the actual golden medallion. And I saw Albert Einstein's name and I said, I'm not worthy. And I said, Barry, come on, you must know that he must have felt that somebody else was, his superior, probably Isaac Newton. And in your book, in chapter 2, you point out that Albert Einstein called, Isaac Newton basically the greatest contributor to Western culture, in history. And then you go one step further and you say Isaac Newton basically didn't speak about what physicists were, but he spoke about God. And he was sort of, he had imposter syndrome about Jesus Christ Almighty. And it's just interesting to me because, the universe or God speaks in numbers. And there's a quote by a mathematician, that God created the integers and all the rest is Menschenwerk. I forget. My father was a mathematician. He used to say things like that to me. But my question to you, first of all, is does the universe speak in integers or real numbers, irrational numbers?
Well,
what do you think?
I've got to say here that if I were a more ambitious person in terms of just putting out there exactly what I mean, I would say that I was alluding there to a sentiment of Dirac's, which is that the universe speaks in mathematics. Right now, I ask for your one's indulgence on this. You may not think that there's a big difference. What I'm alluding to there is the idea that we can learn about the universe not just through making observations on it, but also there is another way of learning about it, which is through mathematics. Now, it's very, very important to recognize that physics and mathematics are not the same thing, right? That is really, really important, right? Mm-hmm. The great majority of physicists, right, are not involved in the world of mathematics research per se, and vice versa. But, and this is the point about Dirac, he argued in his great 1939 lecture, which we could talk about here all day, because it is a phenomenally insightful lecture. That if you look at these, what he would call the fundamental theories of nature, so he's thinking about quantum mechanics, theory of the very, very small. He's talking about Einstein's theory of relativity of space and time and gravity. That each time there is an advance, they are framed in terms of what Dirac would say is more and more beautiful mathematics. Now, you don't need to be a genius to say, well, Paul, what do you mean by beautiful mathematics? And that's a fair question. I don't think he gives it a perfect answer, to be honest. He simply says, well, if you don't know what that means, right, I can't help you because mathematicians know what that means. And I've got to say, with the greatest respect to Dirac, I don't think that is a watertight definition. But that said, I still think it's a useful idea, right? Whereby you work with ideas of increasing mathematical power. You could say beauty, universality, and all the things that beauty entails. And it can be, in the right hands, Dirac's, and other great physicists, Einstein in particular, had similar views, which we could talk about. Mathematics can be a lodestar which guides you in the right direction. Let me be clear that just working on mathematics will not get you to your most ambitious theories. Just working on that. It takes an enormous amount of skill and judgment in order to bring together both of those things. Very, very few people can do that. And the problem is today, that has been a theme of your podcast, but maybe not stated always very explicitly, but we're in a very, very odd time at the moment in the kind of physics we're talking about, because we found, to what you could say consternation of physicists, that the standard model of the subatomic forces works much, much better than we ever dreamed it would do. So much better that this incredible machine that our experimentalist friends have brilliantly made has really only given us, so far, it's gifted us a proof, so to speak, of the existence of the Higgs particle, the last brick in the wall, so to speak, of the standard model. But to the amazement of people, it hasn't shown up these extra this richer structure at higher energies. So that is why, very broadly speaking, without those clues which we so yearned for, right? That many leading physicists, including Nima is one of them, there's many others, are working on parts of physics where they're guided, as well as what we already know, by beautiful mathematics. Now, let me just say, it'd be much better. I've said in book reviews before, people, if we had a choice, it's a silly thing to say, but you'll know what I'm getting at. If we had a choice now between another Einstein or another Rutherford, right? We take the Rutherford, because we really, really need more experimental clues. And it has been, Nima berates me for saying this, but, I think most physicists would say it's been very disappointing, saddening. Nima, let him speak for himself, but I think he'd say, no, nature is telling you something. You've got to be smart, right? But we're in a difficult place. I can't remember a time like this since the beginning of theoretical physics, where, so many elite physicists are struggling to know which way to proceed. And that's why there's been this culture now of naysayers coming out saying, no, all the best people are all getting it all wrong, right? That gap has been has been filled by these outriders.
And I wonder, from the experimentalist point of view, first of all, I thank you, and I'll Venmo you some cash for the plug for experimental physics. First of all, we're looking toward the heavens now, and I wonder, what you would make of it, or what theorists would make of it. If for the very first time in history, a cosmologist or an astronomer would tell an elementary particle physicist the mass of a fundamental particle like the neutrino. That seems to be, Chern just came out with an upper limit of order the electron volt for the mass sum total of neutrinos, and I'm like, welcome to 2005 in the cosmic microwave background. No, congratulations to them. It's a wonderful laboratory-based result. It's incredibly painstaking. But we're far ahead of that. We're in the milli-electron volt, hundreds of milli-electron volt regime, and we're going to do better with Simons Observatory and cosmic microwave background experiments to come. But when I hear theorists kind of do things like, well, we need a future experimental collider or something like that to test my theory of everything, be it my friend Eric Weinstein, or loop quantum gravity in the form of Carlo Rovelli, who's been on the show, or Lee Smolin, or any of these folks, or Nima when he comes on the show. I often say, well, imagine if I had went back 20 years ago, Graham, and I said to you, how about this? I can't build you a bigger, better Large Hadron Collider just yet, but I can smash together two 30 solar mass objects comprised of pure neutronic material at half the speed of light, and I can do that and I can do that, and I can record that many times, and I can give you an atom smasher that smashes together 10 to the 59th atoms of pure hadronic material. How about that? Can you make some predictions as what your theory would say? And they all say, well, in other words, when Newton was thinking about the unification of color theory, he could go and blank out parts of the spectrum, and he could look at the low energy limit, and he could use that later to think about unification. How come theorists are not thinking about the low energy limit as a clue to what the high energy frontier might yield? Could we even approach it?
Well, I take your point Steve Weinberg once commented to me that the frontiers at the moment look like they're in astrophysics and cosmology, with all these incredible results, like the increasing acceleration of the universe. What a result that was! Nobody ordered that. I'm afraid I'm old enough to remember when the Standard Model was being basically formed. With your Weinberg, your Wilczeks, and Grosses, and many other people there, right? And it was an incredible experience. It really was an incredible experience to me. I remember, for example, people saying, I could give you several examples. With one, not in the Standard Model, but I remember Ron Drever, in my first academic job, coming and giving a talk, and people laughing at the thought of detecting gravitational waves. Right? I can remember very clearly meetings at the Royal Society where people were saying that the third lepton, right? Well, come on, but Marty Pearl wants a Nobel Prize and what have you, all right? And we know what happened, right? I've seen this where people, and of course, I remember when reading about Rudy Piles, where he was one of the great theorists of the war years and soon afterwards, saying that no one's actually going to detect the neutrino. That's just not going to be on, and that's why I'm reluctant ever to say that we'll never be able to test this. We'll never be able to do these very high energy experiments because you never know what is round the corner.
Yeah. So one of my heroes and friends that I'm blessed to know is Chern-Simons, who plays a very important role in this book. I've tried to get Frank Yang on the podcast as well. He's quite elderly, as you know. And you describe in the book, and the book is so delightful, you describe the role of Frank and Chern-Simons as sort of this interesting role that I believe is sort of echoed later, although amplified certainly by Ed Witten, as sort of a catalyst, bridging together the older generation in the form of the rack and maybe with genetic material in some sense of Maxwell, and then literally in the form of Yang and Mills, basically on steroids, the Maxwell equations, and then later inculcating it with the Chern-Simons. Can you say something about where is Witten in all this now? Of course, with large, nowadays I see him on Twitter and so forth, and he's talking about Israel, basically all the time. I'm wondering, where is he getting any time to do any string theory or any work? But I haven't seen, and his most recent papers are about maybe Planet 9 is a black hole. Has he given up? I mean, what's going on with Witten these days? And is anyone playing the catalytic role that he once played or Chern-Simons is once played?
Well, I think, again, I feel a little bit, I've got to answer your question out of courtesy, but I feel a bit bad speculating on what Edward is doing. I will say that he is very carefully spoken. He knows that people like me, and I dare say your good self, take a lot of notice. On my podcast, when I put that one up, it practically broke my server.
Yeah.
Everybody listened to and he is really worth listening. I mean, to quote Weinberg, Edward is deep, right?
Yeah.
Now,
no, it's a phenomenal episode.
He is.
And we'll have a link to it in our notes.
He doesn't throw around these words, these big. And I think I know people. We want that from the leaders, the preeminent people in our field. But he's very, very careful. I certainly have heard him say, right, that picking up the point we discussed just a few minutes ago. It's difficult. It's difficult to know what to do in the face of what we're seeing at the LHC, right? Now, that's not because people like him are not brilliant. It's because it's not. We really weren't ready for that for this outcome. Outcome is perhaps the wrong word, but the findings of the Large Hadron Collider. Maybe it's all going to end. Maybe somebody's going to show up next week. But at the moment, it's starting to look like we're not going to be finding these these wonderful things, phenomena that we were hoping for. I remember, incidentally, there's one little thing before I come back to Edward, that I was one of the people that worked on the draft of the public relations strategy of the Large Hadron Collider.
Oh, wow.
And I was, for the British Research Council, and I was looking at that document the other day. Right, it's an internal document, but we canvassed the very best physicists asked them what they were expecting from the Large Hadron Collider, right? And I have to say, I think we broke down something like a dozen things that might, large extra dimensions, supersymmetry, of course, right? And what did we found? We found that the Higgs particle.
Yep, and that's it.
That's it, right? Now, please, I'm talking to an experimenter here. This is absolutely not to put down the fantastic experimental work that has been done to get those things. But my goodness gracious, we really did. So far, maybe things change next week, but so far, we really have got very little out of additional value out of it. Now, I think, going back to Edward, as I said, with apologies to him if he ever hears this, people like me shouldn't be summarising what Witten says, but I suspect he's saying I don't have a useful suggestion about what to do next, right? What he did say to me, it's in my podcast, I treasure the quote because it is so powerful, that I asked him, right, about, whether he thought string theory had, that I mean M theory by that, but the generalised string theory, right, about other options. And he said, right, and I remember very carefully, I listened to it so carefully, right, is that string theory is the only interesting generalization of Yang-Mills' quantum field theory. Right? Now, if I were working on loop quantum gravity, which he just says is just words, right, I'd be very, very worried. Right? He's the last person in the world you regard as a fool in these things, the last person in the world, right, that you would regard as somebody who's a simplistic thinker. But I think that to me is quite important. Because he's saying that something that you hear from many experts. I don't think he would use these same words, but many people, when I was writing the Universe Big Two Numbers, who were saying to me, the biggest problem we have, right, with string theory is we just don't fully understand it. Right? Yes. They certainly don't want to write it off. They know they've got serious problems, of course, but it's the only interesting option that we have, right? But that said, I do think it fair to say, in all generosity, right, that after the incredible fanfare that string theory had in the 80s, when with the first string revolution, the second one where Edward did that incredible work, and then with the developed in the late 90s, it's very difficult to identify in a clear, communicable way the progress that we're making with that field. Not to say you throw it away, but it's not easy to how can I put it, to say, well, we solved this problem, basically everything is sorted out. Right. So that's why I think we're in a difficult position on this.
Yeah, I agree. And to that extent, I feel there is some glibness on the part of folks like Michio Kaku, who will, rightfully say that he is the father of, string field theory. And he wrote down some of the first, Feynman diagrams in the early 70s. And I reviewed those on the interview I did with him. But then he'll go, turn around and say, if we get this, we'll know the mind of God. And your countryman, Stephen Hawking, also was no stranger to hyperbole about string theory, M theory, even to the point of conceding bets willy-nilly. I wish I did meet him once. I heard him speak once, and that was wonderful at a Royal Society meeting in 1995. I'll treasure that.
I heard about that in your earlier podcast, yeah.
Yeah, but the fact is, he would always concede these bets long before I think, he should have. Maybe it was for the publicity of conceding bet. Stevens concedes a bet because they were conceded on the basis of, calculations in 5-dimensional ADS CFT by Juan Maldacena or something, which is, so far removed from any kind of experimental verification. I mean, I think it's, as some have said, it's impossible to deny that it could be that black holes preserve information, but you can't necessarily confirm it. So fellow guest Leonard Susskind has said, this is my battle to preserve quantum mechanics. Well, who knows? But when Michio says things like this, the mind of God, and quotes that at the end of his book, I think it does a disservice, because ultimately beauty, as Ed is saying, implicit is subjective. And as He's saying it's interesting. That's a euphemism for beauty, or there's something that piques his fancy. And as my namesake, the poet Keats said, "Beauty is truth, truth beauty. That is all ye need know on earth, and all ye need to know." And actually, Dirac, echoed that. The only time I think that he used referred to God, he was not a religious man by any means, as you know. He said, "God is a mathematician of a very high order," as you've said this, Graham, so you know this. But I'm saying for my listeners who may not know Graham's wonderful words on Dirac, and I recommend it. God is a mathematician of a very high order. And he used very advanced mathematics in constructing the universe. So I think it's interesting that we do this, but we also don't necessarily have a rubric or a criteria set for how do we judge these theories? How do we, beauty is one thing, but I don't know if you've ever seen this, Graham, but they've done studies on who is handsome, who is beautiful. So they take Brad Pitt. So he's reputedly the most handsome man on earth. Okay, present company excluded. Okay, Graham. So they'll take Brad Pitt, but then they'll say they'll take his face and they'll divide it down the middle. They'll take a picture of him, and then they'll mirror image, they'll reflect his left side to his right side, and then that'll be a new face. Mm-hmm. He looks grotesque. He looks hideous. Nobody wants to look at it, and he'll be the ugliest man on earth. So symmetry is ugly. And actually, it's the broken symmetry that we find beautiful and allows us to live, as you point out in this book. The broken symmetry is what's actually beautiful about the world. If perfect symmetry would be perfect, entropy, we wouldn't exist. So we would have equilibrium. So why is it that beauty? I don't think beauty should necessarily be a condition of. It might work for Keats and poetry, but not necessarily for physics. So. What do you make of this? Should we have a rubric that we apply? At the end of your book, you come up with 6 ideas that you think will stand the test of time from our modern era. But let's start right now. What kind of a rubric could we put forth for grading candidate theories of everything? What would count? What would you put in such a rubric?
Yeah, wow, it's a good question. It's a pretty tough. Let me just. I'll come back to it. I promise.
Yeah,
if I don't.
Sure.
Come and get back to me. I just want to say that I think the mind of God. When I read that sentence in Hawking's book, I thought that's an inspired last line. And you're an author. I bet, as an author, you would know what, right? Because somehow it has a kind of it's poetic, and it's a metaphor, right? Sure. It is absolutely, of course, it is not a literal statement, right?
Correct.
Now, I simply say that by overusing it, it is actually borderline silly, frankly, to try to make that more than it is, right? Mm-hmm. I think most people, even if they're not physicists, if you describe to them basically what physicists are trying to do, understanding these different interactions in terms of mathematical theories, if you have a theory, you can explain all these things, people know, yeah, I get what you mean. And it's somehow, it's a satisfying way of summarizing it. But to try to talk about that as a desideratum, right, mm-hmm. to me is, well, you wouldn't get Edward Witten saying that. I'll tell you now, you really wouldn't. Now, in terms of the progress we make, right, the first thing is not to be sniffed at, in my view. Right, you absolutely must, in the standard way in science, you have to generate all the successful predictions, right, that have been made by theories before. And that is why the essential guide rails of people working in this field are quantum mechanics and relativity, right? Now, it's something that I tried to emphasize in that book. Perhaps I didn't do it enough, right? Because it's still not spoken about enough, in my opinion, is that if I were asked, right, what is the central lesson of the late 20th century theoretical physics, I would say it is the astonishing power, right, of yoking together what look like the most unlikely of bedfellows, which are relativity and quantum mechanics. They look completely different mathematically. They are different of nature. We know that. One's a classical theory, one, of course, is quantum. They're not the same thing. And if you do something, right, as bold as to try to bring them together, right? And Dirac, I believe, was the first person to start on that road. Many others worked on that, right? Then the key thing is to say that if you want to set out a quantum field theory of the interaction between charged particles like electrons and photons, for example, right? It's Steve Weinberg stresses in his quantum field theory book. It's incredibly difficult to do. It really is only just possible. Now, that's a really important thing to understand. It's not just a question of whether this is easy to bring these two things together, right? It's extremely difficult. It's almost like you're going on a razor's edge, so to speak. And yet, that theory, right, you're talking about here Dirac and Heisenberg and several other authors, then made usable by Dyson, Schwinger, Feynman, Tominaga, right? That theory is umpteen decimal places, right? Now, that is telling you something, right? It is saying that these two improbable theories, when brought together, are putting you in the right direction. And you look at the other great successes of those two things. Of course, the Dirac's prediction of the anti-electron, the antimatter, came out of quantum mechanics and relativity, right? Hawking's greatest triumph came from taking general relativity and brilliantly working with in a way that isn't actually a unification, but is if you like, a jamming together, ingenious jamming together of quantum mechanics and an Einstein's theory of gravity, and of course the modern quantum field theory of all the subatomic forces. They're all based on those things, and that is incredibly difficult to do. It's something that, as I said, I don't think it's stressed nearly enough. Physicists don't just sit down and write any old theories down. They have to stick to these two giant foundation stones.
Right. Yeah. As Nima says, it's very hard to break the standard model of quantum mechanics.
Absolutely right.
But actually, I use that, Graham. That's part of my rubric. So I look for, I study, the cosmic microwave background. And within that, I used to think the greatest trophy of all would be gravitational waves and detecting B-mode polarization from the putative inflationary origin of the universe. Of course, I wouldn't turn that down. And some say, been there, done that. Of course, we had to retract and recant, as you know, better than anyone probably besides me. This would cause great sensation. But the quest that really motivates me now is the search potentially for small departures from our most cherished symmetries, Lorentz invariants, perhaps primordial magnetism, phase transitions. These are ways that we can, in Nima's words, break the standard model, but they must be subtle. They must be subtle, but maybe as the Lord is not malicious, right? So those are, it's very hard to do, and that is part of the rubric that I think becomes very hard to. So we're the low hanging fruit has been picked, and so we're left with beating our head and grinding our head against granite. But I guess the question becomes, are there low energy ways? So the CMB is a low energy phenomenon. It's 3 Kelvin photons, but they trace the properties potentially of a very high energy phenomenon, and that's what makes it interesting to me. So my hope is that are there other ways that we can look, machine learning, are there exoplanet? I don't know. There's some signature using cosmic data, perhaps, or laboratory data, microgravity scales to test departures from the standard model, indicative to grade these theories. Because when I talk to Michio or I talk to proponents of string theory, they say things like, well, how is it possible that, like when I complain about the multiverse aspects of string theory, well, how many solutions are there to Maxwell's equations? There's an infinite number. You have to tell us the boundary conditions, the initial conditions. Okay, well, I can tell you boundary conditions from physical observation, but you can't retrodict and use that as a prediction. For example, G-2 results came out, LHCb results.
Well,
Michio he was claiming those are come as results of string theory. I said, come on, how can that be? How can that be? You can't claim everything, right? And you can't simultaneously say, you have to tell me the vacuum state. Why is that my job as the experimentalist? Shouldn't that be the outcome of the theory?
No. To me, the more I look at the history of this subject, I really commend the position of the conservative revolutionary. Right? And if we start off with the first theoretical physicist, I mean, I know that's a subjective matter, but a very good choice for that is Max Planck, right? And I admit, I mean, this is being fanciful. I accept that, but I'm will always be fascinated with this extremely conservative physicist, right? Who was, told by his supervisor, I believe it was, that, there's nothing to be learned now in physics. Basically, we've got the basic rules. And then he took what is is a very good example of the most dramatic step, right, in proposing that radiation comes in quanta, right? And to quote Bram Pais, right, the mathematics of doing that was mad, right? I mean, even if you're a passable college student, right, of physics, could see that basically it pretty much made no sense, right? But he was right? Yes. And it took Einstein then to take it on another step forward and beautifully clarify what he meant by that. This is the point where I'm going to speculate, and like most speculation, is probably wrong, but I'll be interested in your views on it. That, I just wonder whether we're missing something, some insight, right? That is as radical as revolutionary, right, as that contribution of Planck's was. Is all this confusion? Could it be resolved? I'm not saying in a trice, but are we missing something really, really big? Right now, as I said, obviously it may be nonsense, but I just wonder, the state we're in, whether we are just missing something.
I was thinking about that as I was reading it, and I couldn't help but just imagine the amount of, obviously progress is usually, there's a paper called Progress by Compression. It's a wonderful paper, and one of the culminations of it is, think about how much compression is involved in Einstein's E equals mc squared, like how much information, how much notions about reality are compressed into that. And I think that's true. And then, of course, think of how many books are needed to explain what is the meaning of that. And then it's like expansion. But now think the opposite way, Graham. Think like 1901, Planck, 1900, 1901, Planck Nobel Prize for, a three-symbol equation, E equals h nu, or E equals hf, or, and then Einstein later, he didn't win the Nobel Prize for it, but E equals mc squared, four symbols, and now it's like Nima and his colleague, and it's like 100 pages of mathematical formulae. And I'm wondering, like, is this going in the right direction, or is that just a symbol that the low-hanging fruit have been picked? And it is curious to me, I can't tell. I don't know. When I look at things, so I do like to ask the people that like the Kakus, because I do think that he has interesting insights. So I said to him, here are some interesting arguments from critics of string theory: Lee Smolin, Carlo Rovelli. And by the way, these are people that you don't necessarily agree with. You believe that the tradition
we thrive on agreement in physics. Yep.
Yeah, but you're obviously you get along and you don't necessarily there's no hard feelings. You're just criticizing. No. Yeah, but Michio is much more aggressive. I think he's saying, well, look, there's nothing in their theory. They don't even have fermions. They're doing something. Maybe it's gravity, but it's not a theory of everything the way string theory is. String theory can give you, the elephant, and it can wiggle its tail. A string theory can give you the 1-inch equation. It can give you even mathematics. And my thing to him was, well, can it do over much? Can because of this vacuum problem, is there not a danger that the laws of physics might be different in each one of these landscape universes, but maybe the laws of logic, maybe the laws of mathematics? In other words, how is it that you're guaranteed to have a self-consistent form, modus tollens? Is it going to agree in a universe, a landscape where even these dimensions, we don't necessarily have evidence that they agree? Mm-hmm. And he couldn't really answer that, except to say that in string theory, you get gravity out naturally. But again, I said, we don't have evidence for these large dimensions. And so my question is it not already falsified? And his basic response is, it's too early to say that, and all the other candidate theories, as Witten would say, are uninteresting, and if not already wrong.
Mm-hmm. Mm-hmm. Well, I do think, personally, I respect his point of view, and his heart's in the right place. But I do think that he's almost like he's in the 80s, where that sense of almost triumphalism in string theory. But to say that now, when there are so many challenges besetting the theory, you can't really blame people for being skeptical, right? because, I mean, I know this might sound naive, but in the end, the plain person is going to want to know, right, why should I believe in this, right?
Yes. Yes.
Now, I do think we owe people who are not physicists at least indications of why we take string theory seriously. And as I said, that quote of Edwards, it's the most interesting generalization of an obviously successful Yang-Mills field theory. At least that is at least clear about what it is. But there are so many things that string theory hasn't done. For example, it hasn't retro-explained things. I think I'm right in saying that you can't take problems in the physics of fundamental particles that were explained by string theory backwards, so to speak. Right? Steve Weinberg mentioned that. At least that's my understanding of it when I spoke to him about this. So, I think, I think there's a cultural thing here, Brian, because, we're in an age where everyone can be an expert for a start. Everyone can have a view on anything, right? And as I mentioned at the end of my book, I don't wish to be mean-spirited, but, I think that, that we've lost this deference for authority. Authority, and I don't just mean that we should worship the most famous Harvard professor or what have you. No, we shouldn't, right? But I think we should have at least a respect for why parts of the community are spending so much time on that. And I think there is another point, if I could just be critical for a second, I think personally it's regrettable that a sober, thoughtful response from string theorists to these critics isn't more forthcoming. I think that's a real shame. I think I know why they do it, incidentally, although I'm not going to name any names. That it's like Richard Dawkins when he stopped talking to creationists, right? And that was because he said you simply can't win. You simply can't win. Now, I still think maybe I'm old-fashioned, but I think that there is plenty of room for a small number of forums where the people who people who are very doubtful about the way that string theory is going can talk to their critics in a way. Now, it's not easy to do. Let me say, this is not a trivial thing. But at the moment, I see very few examples of where very articulate people on the public stage, like Sabina, for example, like Lee and what have you, actually talk in a respectful, straightforward way, right? Instead, it's done through intermediaries,
right? Or on Twitter,
on Twitter, and I don't think that's helpful. I tell you, I honestly can't think. It may be my ignorance, but I've thought a fair bit about this. I can't think of another stage in physics where it's been like that. I really can't, right? And nor can I think of a time, maybe it's related, where people who the community of theoreticians would say are the world's leading people are just routinely dissed. Right, as if they just don't know what they're talking about. They just I mean, it's an incredible situation, right?
Again, I'm reading your book, and I just love this book so much, Graham. I want to just reset the conversation for a second. This is The Universe Speaks in Numbers. Graham Farmelo, who's just a delight to speak to, the author of several books, Strangest Man, about Paul Dirac, who we'll have back on again. That won the Los Angeles Times Book Prize. He's a fellow at the Churchill College at the University of Cambridge. His book about Churchill, bomb. Churchill's a fascinating character. I love Winston Churchill. My 9-year-old, 10-year-old was reading his 1,000-page autobiography recently.
Tell your 9-year-old to read Hawking. Sorry, that's my present project. I'm sorry about that. But beg your pardon. But Churchill's best book, which was actually alluded to in his Nobel citation, was a book your 9-year-old could read called My Early Life.
Okay.
Right? A 9-year-old could read. It's a charming book, and it's about his youth.
I can't wait.
It's a lovely read. And I say again, the Nobel people had that in mind when they gave him his prize.
I will certainly refer that to him. Yeah. And then of course he is a regular visitor at the Institute for Advanced Studies in non-pandemic times, I assume, and he will get back there, and I will hopefully have him someday. Graham, you'll come and visit me in San Diego, where this office used to be occupied by Jeff Burbidge. And Margaret Burbidge. We'll talk a little bit about that. That segues nicely, maybe perhaps into the conversation we were just talking about, these weird times that we live in. And I was thinking, you talk in the book about Maxwell and how he came up with this mechanical model of how light would propagate, and he used these gears and wheels and vortices and stuff. And can you imagine what would have happened if Twitter were around back then? And he would have had this, hashtag trending, this fool, these gears, this idiot thinks this Scottish Scotsman.
No, that is a really good point. Actually, it's a really good point, because if you look at the classic article that Maxwell wrote, which I spent a few pages in the university was talking about the relationship between physics and mathematics. He talks about a theory of electricity. He doesn't say, I'm the only one who's right. No, everybody else is wrong. All those German guys don't know what they're talking about. He simply says, and he turned out to be right. The poor guy was dead before we knew that.
Right. He died so young.
You raise a good point there. But if Twitter had been around there, I know that this is what do they call it, bending reality. But people simply said, all right, it's a theory that Maxwell has got here. He is a brilliant theoretician. Remember, he wasn't a physicist. They've never called him a physicist. He called himself a natural philosopher or a mathematical philosopher. But it was not this this bum fight, so to speak, about that.
And that's an example of even what Karl Popper, I always say that physicists, just as biologists have physics envy, and it is said, I believe that physicists have, Gödel envy or mathematician envy, because we can't, really bound what we can't prove. So, Popper kind of substitutes falsification, demarcation, hypothesis substitutes for Gödel's incompleteness theorem. But even Popper himself said there is a place for the unfalsifiable, because there is room for the development of a known wrong theory to kind of blossom and bloom, because if nothing else, it sharpens the correct eventual emergent theory, and that took place in this very room with Jeff Burbidge and the quasi-steady state theory, which prevailed. As you probably know, the companion paper that Dickey, Peebles, Roll, and Wilkinson put out to the Penzias and Wilson paper doesn't mention the Big Bang at all. It mentions a cyclic, collapsing universe basically as the origin of the thermal relic, background. It doesn't mention the Big Bang. And obviously we don't believe that to be the case. And so too with Maxwell, if people had, this is ridiculous, vortices, or, so maybe right now we're, some of my colleagues and even I on occasion will be too quick to sacrifice string theory on the altar of a falsifiability currently. But I think, the challenge that I have as an experimentalist is there's only so many resources. And again, Michio's not here to defend himself. But I said, if you're the head of the NSF, there's only so many dollars to go around. There's only so many postdocs to go around. And it's not fair to a young person, when they might get their first research grant, at age 41 or 42 here in the U.S. I don't know how it works in the UK, but it's very challenging, very competitive. It's a bloodthirsty race here. But to get it, very few positions, 400 applicants for one job, maybe at a place like UC San Diego. And you get, it's a very long delayed gratification. So what are you going to tell them, Michio? Should we let loop quantum gravity and string theory, should we give equal amounts of money? What about to experiment? And he's like, yeah, just give equal amounts of money. And I don't know. I mean, if we're how do you divide up finite resources? How do you engage, the community so that young people have something productive to do? Do we have too many people doing string theory? I mean, Eric Weinstein has said that explicitly, and you should know he's a big fan of yours. But he said explicitly, there's too many people. It's sucking the life out of it. And you probably heard the interview, and Lee Smolin sort of agreed.
I must say on that one that I'm not involved in these hiring committee things, but I've heard enough people, from Freeman Dyson to Martin Rees and other people. It's a widespread view that it's a very, very tough field, string theory. And I think there is a case that you can never be sure. You're never sure when you fund research. But if you ask the proportion of people working on that field, right, is it too high? Then I suspect it might be, right? Because, you really have to be, very advanced mathematically, as well as have physical, and you aren't working with these constant prompts of observation and experiment. So I don't want to be disloyal to my string theory friends, but I do, and I think you have a point too. You never know. It's very, very difficult to know what to invest money into in physics. I'm certainly persuaded that we need another accelerator to study the Higgs much more carefully, but That said, I appreciate the difficulty because governments, funding agencies, they want to see, bang for their bucks. And, out of the Large Hadron Collider, they've had one bang, to put it very crudely, right? Now, that is, let me be very clear. I definitely invested in the accelerator. But, we have to be real. Even Feynman, I noticed in my research, the University speaks in numbers, even he said, which I think is right, it's a depressing thought, but we have to face it. It may be that one day we run out of money to do to do these high energy experiments. I'm sorry if that depresses people, but Feynman's a great physicist, and I don't think it's an unreasonable thing to worry about, right? But nonetheless, it's too early to think like that, in my opinion.
Yeah, I've often thought about that as my role as an experimentalist is kind of be like Galileo's assayer, to kind of to look through and to see what low hanging fruit might remain, and it might be might be our as you talk about at the end of the book, our silicon friends are the artificial physicists. So I've started a project very slowly going called Galileo, where I'm trying to, program the works of Galileo, the text of his books. He wrote millions of words and dumped them into a general AI program and try to, teach it very slowly, quantum mechanics and so forth over the years, and see what pops out of the great mind, because he was certainly a unique intellect. And I want to close out with two unique intellects, one of whom I had on the podcast before he passed away, and that was my friend Freeman Dyson.
You had Freeman. Oh, great.
Yes, many times. He was my first guest on the Impossible podcast. Let's talk about Freeman. What did he mean to you? You talk about him. So he was sort of this voice of reason. I want to relay a quote to you. What he and I talked about, and it's kind of an animating quote in my life, inside and outside of physics. And it was about God. We were talking about God and religion, and he kind of called himself an agnostic, and I used to chide him about that. He's such a lovable person, and one of my favorite memories is we'd have him over for Shabbat dinner. We're Jewish, and he'd come over, and then my now 8-year-old, is basically 90 years younger than Freeman and Imna, and they would talk, and it was just funny seeing like 9 decades difference, and they would just like have these really interesting conversations. And at one point I said to him, well, Freeman, why do you have this interest in religion? Why don't you just either not go or not say you're an atheist because you don't go to church? Like, you don't go to the same church that Richard Dawkins doesn't go to. So, like, why don't you just call yourself an atheist? And he's like, well, there are things in life that are mysteries, and there are things in life that are puzzles. And, to me, puzzles can be solved. You might not be able to solve them, but there are solutions, and somebody smarter than me or smarter than you can solve them. But then there are mysteries, and mysteries may not have a solution, but that doesn't stop me from wrestling with them. And so my goal in life, I've started to think about, like, my goal is to turn as many mysteries into puzzles as possible. Like, that's kind of my mission statement. And I want to ask you, like, what mysteries are you most engaged with now? You talked about working on a book about Stephen Hawking. I'm really curious, and of course I'll invite you back in a heartbeat to talk about that. But what mysteries and what did Freeman mean to you personally? And then we'll close out by talking about Nima. I can't resist.
Well, Freeman, when you say I got to know him well, I'm not sure anyone really understood Freeman, but he was an incredible character, and I had spent dozens and dozens of hours talking to him. First thing to say, right, is to actually let him describe himself, right? I've written a Remembering Freeman Dyson article on my website. I wrote just a few days after he died, and I'm sure I began with this. But he said to me, and he said it elsewhere, that he was only good at two things, which is solving problems and writing essays. Now, I scoffed, right? I think forgivably, right? And he said, and I said something like that. That's ridiculous, or something like that. And he said, it may sound ridiculous, but it's true. And I remember him actually saying that, right? And he was quite a superb mathematical physicist. Make no mistake, and a brilliant, probably my favorite writer. Right, yes. in physics. I mean, the most silken style, right? So he meant a lot to me. I do admit I found it frustrating sometimes with his contrarianism, right?
Yes.
And he definitely had that, right?
Mm-hmm.
I had got a kind of amateur theory here that I think he was so smart, Freeman, that it would be because most people he met, including all these other luminaries in physics, right, he could find a way round what they were saying, right? So it was almost a game to him to say, for example, that Churchill was the second best leader Britain had in the wartime. Who's the best, Freeman? Oh, Neville Chamberlain. Right? Oh, there are dozens of others like that, right? And he would then hit you with the thing that you hadn't thought of, a new perspective, right? With string, what was particularly interesting, I thought, was in his approach to physics. Right, he thought the Large Hadron Collider was not a good use of money. He thought there were far too many people working in string theory, which we covered. He was always looking to provoke. Right, he loved that. Right, and in Princeton, there's a statement you often hear in the Princeton community. Right, is namely that that Freeman would rather be interesting than right. That I think is very perceptive, right? Yeah. He liked the the game of conversation. And I really believe that's a profound thing to say about him. You know, he wanted to be interesting, right? Ever being right, you know, that's a difficult thing for him. What was your other question about you asked about?
Oh, yeah, it'll be about Nima. But before we move on to that, I do want to say, so when I was writing my book, I didn't know if I was going to write any more books, and I wanted to get some star power blurbs on the back of the book. And so I asked Freeman, and it was right after my third child was born, my first daughter. And I wrote Freeman. I said, "Dear Freeman, can you please do me the honor of writing a blurb for this book? It's about losing the Nobel Prize, a subject that, I thought he'd have some strong opinions about." I said, "Dear Brian, congratulations on getting the book done, and my love to your daughter, Orly. My problem with blurbs is that I have a strict rule not to write blurbs unless I've actually read the book."
Yeah, that's right. He told me that.
Yep, and I already have a big pile of unread books. The idea is that a blurb is supposed to be an honest expression of information for the reader, not just a favor for the writer. Perhaps it's a silly, old-fashioned idea. Anyway, I hope the book does well without my help. Yours forever.
Yep, that's absolutely classic Freeman.
And you know what? I've used that. And so now, as you have done and I have done, after you write a book, you get asked to write blurbs for people's books. So I got asked to write blurbs for books after my book. And I got a book in the mail just about back in early December. And it was a book. It was about this thick, about 590 pages long, and it was about intelligent design. But it was by a Cambridge man by the name of Stephen Meyer, and he's a PhD in philosophy from Cambridge, and he writes about intelligent design. And I've heard of him before. And he had written me, would you do me the honor of writing a blurb about this book called "The Return of the God Hypothesis"? And it's about entropy and so forth. And I'll put links to that in the show notes and whatever. And I said, and he said, and could you do the blurb by next week?
What?
Kidding me? So I said to him, "Look, Stephen, I like the idea, but I have this rule that I inherited from my friend, the late great Freeman Dyson." So Freeman has got me out of a lot of sticky palavers, as you might say, over there across the pond. The last question I have is about Nima, and he figures very prominently in the book and does provide a so-called blurb on the back of the book. And he is after you, is the most requested guest on the Into the Impossible podcast. He calls this book, The Universe Speaks in Numbers, a riveting account of one of the greatest stories of our time. Graham Farmelo has delved in deep into this fascinating subject, combining original scholarship and lively interviews with contemporary theorists at its forefront of the field. The result is a masterful book which gives us for the first time a behind-the-scenes look at how physicists and mathematicians, driven by their pursuit of the ultimate truth, capital T, have been drawn into the common territory by their mysterious intellectual forces seemingly beyond their control. His blurb kind of, I'm going to encourage him to write a book. He's a spectacular writer.
And he insisted on that capital T. When my publishers say, no, it's got to be, he said, no, I want capital T.
I want to tie, him and this capital T, because it kind of brought up a beautiful sentence that you kind of maybe put off. Maybe it was a throwaway line, but it stuck out to me like a phone call during a glass of wine. And it was, you say, even in mathematics, ignorance can be a virtue. And I think about someone like Nima as just like this mathematical god. He thinks of himself as a mathematician trained in Toronto, et cetera. What did you mean by that? And can somebody like Nima be considered to be ignorant of mathematics? It seems like we have to be like a.
Yeah, you say that. I think Nima. I've had loads of conversation with him. Amazing physicist, wonderful person. The key thing about him is he's a physicist down to his toes and his fingers. Right, that's what he is. He's absolutely driven to understand the underlying order of the universe, basically. Right, and there is absolutely, his passion. He wears his passion on his sleeve, so to speak. Now, it's very important to when thinking about Nima, he doesn't do mathematics for the sake of it, right?
No.
I literally I got to know him just after he started at the Institute for Advanced Study, when he basically went in, and I quote him now, like a graduate student into amplitudes, right? Mm-hmm. Scattering amplitudes, which is about, looking mathematically at the very deepest, the scattering between quarks and, fundamental particles, and looking at that lowest level of interaction, describing them using quantum mechanics and relativity, as he's always banging on about, quite rightly. Now, the stuff that he's been driven into, it's been a glorious thing for me as a friend of his to see, he's amazed and he's had to work incredibly hard to get into that mathematics. But he's not doing it to show off, right? He's doing it because he's being led there. He's being pulled by the nose, so to speak, right? Into it. Mm-hmm. And you ask him why, he would say, I'm pretty sure, ask him when you speak to him, it would be a great podcast, right? He will say he's being driven there by the fundamental principles at the heart of quantum field theory, and in particular quantum mechanics and special relativity. They have together, right? And I remember asking him once, right? Are you sure? Are you really saying that occasionally you find yourself veering off quantum mechanics? And he said, yes, that is true. Okay, he said once. He said to me, I even did that this morning. Right? You can check it line by line, right? And that's where, incidentally. The miracle that we have seen in this amplitude stuff that Nima has done so brilliantly, and of course he has many brilliant collaborators who work with him in a very creative way, right? That it's that forcing together of quantum mechanics that has given rise to these mathematical directions, right? It's not done because he just wants to show off, right? It's because he feels it really is relevant to nature. Right, and he's going to be a great guest on your podcast. But again, he wants to understand nature. I tell you a story about amplitude. Somebody told me this, and Nima didn't deny it. When he got into it, and of course he became a senior member of the field very, very fast. Somebody wanted to do make a collaboration with him, and Nima said, "I'll do that, but if something comes up at the LHC, I'm dropping everything and going into that."
Oh yeah.
Now, you see what I'm saying there?
Yeah.
It wasn't a case of him leaving that discipline. Do you see what I mean?
Right. No, he is, and he's been very, very gracious, very, very generous with his time and corresponding with me. But he's clearly deep involved in some very significant work, and he begs, kind of to just forestall the conversation with me. And I've of course I'm going to give him, whatever time he needs. And it might actually work out that I get to see him in person, because I have a meeting out there in a month or so. And I might actually get to do the interview in person, which would be really spectacular.
Yeah, he's a great, in my podcast, it's the only one we split up because it was just uneditable. It was just so great. The level of the depth of it and the enthusiasm was so great.
Oh, it's wonderful.
But he's a wonderful ambassador for the excitement, the continued excitement of physics. At the time when some people are struggling to maintain that.
Yeah, the last person I want to speak about before I have to run and teach myself is kind of in contrast to him is Gerard 't Hooft, I think is how you pronounce his name. I'm hoping to get him on the podcast as well. But he seems to be kind of the the Freeman Dyson like character, the old guard in some sense. And maybe I'll send him this episode to convince him to come on. But what are your impressions of him and where he is? He's still quite active. He has
he is absolutely. I really do believe he's one of the great physicists.
Oh yeah,
I mean, he really is. I mean, you have to take everything he says seriously. He certainly seems to be quite sceptical of modern developments, I think it's fair to say now. And, he's looking at new ways of formulating quantum mechanics, I've noticed how careful he is to say to young people, go and learn it from the standard books. But he's obviously unhappy with the formulation of it. But no, De Hooft is an absolutely, and another one incidentally is his, basically they were like a duo in my time in particle physics, and that's Sasha Polyakov at Princeton University. Those two were basically neck and neck in many ways. I mean, they are both absolutely brilliant physicists. And it's a shame now that, we mustn't patronize them, but, that they were our heroes in the 70s. They were just absolutely teeming. And of course, the thing, what I say to Nima so often, he really doesn't like this, incidentally, right, is don't you sometimes miss that these De Hoofts and Polyakovs and Weinbergs had actual data, right? And he said, no, this is what Nima will say is, we're getting data from the Large Hadron Collider, and it's telling us something. And it's our job, right, to interpret that null result, just like, in a sense, Einstein did with Michelson-Morley, right? No result. That is telling you something, right?
Exactly right. The most famous failed experiment in history, done at my alma mater, Case Western Reserve University.
That history of that is endlessly fascinating. How can a null result, right, be so powerful? But we know it was.
Yep, absolutely. And again, if we had looked at falsification as our only criterion, how backwards things would have been. Farmelo, I want to thank you so much. Tell me, are you going to resume your podcast? It doesn't.
Well, I may do. At the moment, I'm deep in. There's what 25 interviews there. But at the moment, I'm deep in writing the life of Stephen Hawking. So we will see. But for the moment, congratulations on the job you're doing. You produce a wonderful corpus of interviews. So I'm very grateful. There's a lot for us to work through.
Yes. Thank you so much for coming on the show, for being a guest, and for inspiring us with your podcast, and for this wonderful book, and for the book on Churchill. Dirac, we'll have you back. And please do let me know as soon as you're done with the book on Hawking. I'd love to have you on. I had Charles Seif on for his book. You may have read it. You may have seen the interview. It's quite critical. I'd love to have a discussion with you. And maybe we could have a friendly debate with Charles. That would be an interesting kind of a pairing to do if you're up for it. But for now, Graham, thank you so much for spending so much of your valuable time. It's been a delight and a pleasure.
Any sufficiently advanced technology is indistinguishable from magic.
If you enjoyed this video, I know you'll love my conversation with Juan Maldacena, as well as my other conversations with physicists and astronomers. Click here and don't forget to subscribe. Leave a comment in the comment section below. Do you think the universe really speaks in numbers? And if we had another Dirac, another Maxwell, would we recognize him or maybe her? Let me know in the comments below.